Hey guys, I'm Ben, and here's my presentation for how trust factors in to human-robot interaction. The paper I read was, When Humans Aren't Optimal, Robots That Collaborate with Risk-Aware Humans. The challenge that this paper is trying to tackle is how do we predict human behavior when humans make decisions based on risk, and they aren't always rational decisions. So what do we mean by that? Well, here's some background. Most current robots, they're modeled using something called the noisily rational model, which assumes humans as mostly rational. And let's kind of give you an example of the types of the decisions I'm talking about. So let's say you're offered $100 with 100% certainty versus $130 at 80% certainty. Well, I don't know about you, but I'm taking the $100 guaranteed every time. But by doing that, I'm making a risk-averse decision. So how do we break that? Well, take a look at this, the risk-aware model. This is what the paper is all about. It builds upon the noisily rational model and adds something called the cumulative prospect theory of behavioral economics. The point of adding this economic theory is that this behavioral economic theory does a great job at predicting humans acting in a risk way, or considering risk into their equation. So basically, we're taking robots and adding psychology into our model. So let's take a look at both models side by side. So the noisy rational model, it models humans that make rational decisions to maximize rewards. And this fails when humans make suboptimal or risk-averse decisions. While the risk-aware model is designed to predict these suboptimal decisions and predict when humans make rational decisions as well. And so here's a technical approach. Again, don't get freaked out by all the math, but there's a couple things I want to point out. So this is the noisy rational model and the risk-aware. I want you to note how both these models look pretty similar. And another thing I want you to note is there's only 2 lines of math before this model, and there's a bunch more math over here with the risk-aware model. And I watched a TED Talk once where they said the second you show a math equation on your PowerPoint, that you lose the attention of 95% of the audience. So, to gain back some of your attention, here's a picture of a cute robot seal. You got a cute seal here, you got the cute old guy, and hopefully I got a lot of your attention back. So let's take a look at the new equations, which I made in words. So here's the noisy rational model. I said the probability of a specific action equals the reward times that specific action divided by the sum of all rewards and actions. And this reward is relative to this action. Where the risk-aware model, the only difference is I added this CPT component to the reward variable, which basically I just did was I accounted for the behavioral theory of economics into our noisily rational model and made a bigger model. And also note, these look like linear equations, but this is definitely not. However, for the sake of this presentation, I think this is enough understanding. So let's take a look at the first experiment, the autonomous driving experiment. So here's the situation. Humans, this is a human car, and this is the autonomous car. So pretend you're in this car here, and you're driving a rental car, and you're approaching a yellow light. If you choose to stop at this yellow light, you're going to be late returning the rental car and pay some sort of late fee. However, if you decide to accelerate, and you end up running a red light because the yellow light turns red, then you're going to have to pay a $500 ticket. So what are you going to do? Accelerate or stop? Let's see what the models think. Well, the hypothesis, we'll start there actually. Autonomous cars, which use risk-aware models of human drivers, will more accurately predict human action distributions than autonomous cars who treat humans as noisily rational agents. So what does that mean? Basically, the risk-aware model will predict what humans will choose, whether to stop or accelerate, better than the noisy rational model. Here are the variables. The independent variables are the information and time available to the humans when they have to make their decision. The dependent variable is the action distribution that represents the human's decisions. So what did the humans do? And we'll talk about this more on the next slide. So first, the participants in the procedure. The participants. We had 30 participants. All of them had a 95% rating from this website called Amazon Mechanical Turk, which I hadn't heard of before, but doing some research, it seems pretty reputable. And it's interesting, you should check it out. It's for cases kind of like this where you can hire people for sort of random activities. Now let's take a look at the procedure. So it was a within subject study, so all 30 participants were a part of all the situations. And then next, the subjects were shown the situation and then asked if they would stop or accelerate. So the subjects were shown this and explained more or less how I explained it to you, with some differences in terms of information and time. So first, they were asked timed questions, and they were presented in order from not much information to explicit information, where implicit information was given in the middle. And also the risk varied. So let's take another look at that. So with no information, I mean there's just some arbitrary probability the light will turn red. When they were provided implicit information, it was some cars it turned red for, and the explicit probability said there's a 5% chance the light will turn red, where the risk varied over here. So what did they decide? Well, most of them decided to stop. As you can see, where the greens accelerate and the blue is stop. So in both the risk low and the risk high situation, humans chose to stop. And what I want to clarify here is that the risk low situation where you stop is suboptimal or risk averse decision. And again, to clarify even deeper, the risk high situation is defined by where the light would turn like red 95% of the time, and the risk low is the other situation. Now let's take a look at the results. So here's how the models differed and how they performed. So the gray is noisily rational, and the orange is risk aware. So for the high risk situation, both of the models had about the same output. But what's interesting is in this risk low situation where humans acted suboptimally, the noisy rational model just was still a straight linear function. However, the risk aware model overestimated the probability that humans would stop relative to the noisy rational model. And in turn, that was actually correct, as we'll see later on. So how do we verify this statistically? So we'll use the Kullback-Leibler divergence accuracy. And again, this is maybe kind of confusing if you're unfamiliar, but just know that the lower is better. So let's take a look. For the risk high situation, they both performed about the same. But for the risk low situation, we see that the risk aware model did way better than the noisily rational model. And it did so better, in fact, that it had a p-value below 0.001. And this is really statistically significant considering it only needs to be below 0.05 to qualify as statistically significant. So what's the conclusion? Autonomous cars leveraging a risk-aware model were able to, this is really wordy, but basically the risk-aware model was able to predict the rational and suboptimal situation, where the noisy rational model just failed when it came to predicting humans acting suboptimally. So now let's take a look at the collaborative cup stacking experiment. And when I first heard or read this cup stacking, it sounded kind of boring. But then just stacking cups. But then I thought a little deeper about it and how this applies to the real world. And to explain myself, let's take a look at this video. What I want you to notice is how close proximity this robot is acting relative to this human. And you can compare that to robots you see these days, where they're in factories with 10-foot cages and massive alarm systems, and you can't get anywhere near them. So this is really a huge step forward. So there's two experiments in terms of the collaborative cup stacking. The first is the online one. So here are the two situations that the humans had to decide between. To build an inefficient but unstable tower with the robot, but that failed 80% of the time. However, if it didn't fail, they got $105. Or the humans could choose to build the inefficient and stable tower, and only get $20 if the tower doesn't fall, which actually the tower never falls. So they're basically guaranteed $20. The hypothesis here is the risk-aware model will be able to better predict what the humans will do. So let's take a look at the setup. First, talk about the participants, 50 users, 14 from Stanford, 36 from Amazon Mechanical Turk, about 30% female, median age 33. So what are you looking at here? Well, this is kind of the information that was provided to the participants in the online survey. They were showing this video of the unstable tower, where the robot, they showed this 5 times, and the robot only passed one of them. Where building the stable tower, it succeeded every time. And you also might be wondering, what does it mean in terms of efficiency or stability, right? Well, take a look at this. So here's the goal cup. You can see it's the bottom for both these. The idea is all these cups are different sizes, and this is the biggest one. To build the most stable tower, you want to put the next biggest cup on top, and then after that, you want to put the next biggest cup on top. So it goes from biggest to smallest. But if you want to build an unstable tower but faster, you kind of grab the closest cup and do it as fast as you can. You ignore the size. So what are the variables? Well, the independent variables here are the two models we're looking at. The dependent variables are the participants' action distributions. So what did the participants decide? The baseline here is a noisily rational model would anticipate participants to build the unstable tower since there's more reward. What are the results? Well, we have a statistically significant improvement with the noisily rational model. You can see that here with this, we're using the KL accuracy metric again. And you can see that the risk-aware model just absolutely destroyed the noisily rational model. It wasn't even close. And so let's go to the next one. Now we're going to talk about the lab experiment. So let's look at the variables first. We have the models here. And then for the dependent variables, we're testing two things. The efficiency, quantified by completion time and trajectory distance. And then the human subjective response, which was quantified by a survey, which had a list of different things ranging from safety to enjoyment, and we'll take a deeper look at that later. Hypothesis 1, the objective hypothesis. Using the risk-aware robot, we'll complete the task more safely and efficiently with the users. And the subjective hypothesis is users will feel like this risk-aware robot was better to work with all around, and again, we'll look at the parameters later. So, the participants in the procedure. We had 10 participants, 2 of them are female, and 6 of them had no prior experience working with this robot. The procedure was they had 10 familiarization trials. So they're working directly with this robot, and in 5 of those trials, they were given, they're told, now the robot's using the noisily rational model. Or they'll say, now the robot's using the risk-aware model. And these were kind of randomly interspersed between these 10 familiarization trials. And then after that, after working with this robot, they were asked to fill out this survey regarding their experience. So here are the objective results first. So first of all, I want to say these were statistically significant results at p less than 0.05. And I think a better way to explain this is just to talk about these graphs. So let's take a look at this first. Where lower is better for both of these, we got completion time and trajectory length. We'll talk about that more in a second. But gray is noisily rational and risk aware is orange, which is the one we're talking about again. So obviously completing it faster, that's better. And then looking at this, a lower trajectory length. What does that mean? Well, I actually don't like the word length here. I think total distance the robot traveled relative to the trajectory is kind of what they mean by this. As you can see, the risk aware traveled for less distance. And to really get a good idea of what I'm talking about, you can take a look at this picture over here. So here is a rational model, and here is a risk-aware model. There's the robot, here are the cups, and this little thing, this is the participant's hand. So when the rational situation, the rational said, I'm going to pick up this orange cup. And then it sees, oh, wait, crap, there's a human hand here. I can't run into that hand. And it has to readjust its trajectory and pick up the purple cup. Where the risk-aware model right away decided to pick up the purple cup, and the human was able to grab this without this situation happening, which causing the lower trajectory time or trajectory length. So what were the results of the subjective results of the lab experiment? Well, this actually kind of failed. Only the preferred category, which is right here, was a statistically significant improvement over the noisily rational interpretation. So to really clarify this, the participants were asked, how well do they enjoy this 1 to 7? How well they understood the robot and could predict, and how well they could predict it, the efficiency, what one they prefer, how they feel about its accuracy. And again, only preferred did really well. Efficient was almost statistically significant, but they did mention that humans using the noisily rational model, there were said things like, oh wow, the robot almost got in my way, where it was kind of scared me for a second when it went for the same cup I went for, and stuff like that. So they said this hypothesis was partially supported, which is whatever. So here's the conclusion. Both online and in-lab user studies extended our autonomous driving results to a collaborative human-robot domain. They also demonstrated how this model meaningfully adjusts the robot behavior to improve safety and efficiency. So what does that mean? When they refer to extending our autonomous driving results, they're kind of referring to this online experiment from the cup stacking, where it basically predicted what decision will the humans make. Where this in-lab study actually incorporated a robot in it, and that was how it studied safety and efficiency. So this is where the clarifications and limitations. Well, first of all, I do want to say I kind of wish I saw more stuff where the model was actually implemented in the robot instead of just part 2 of the collaborative cup stacking experiment. I wish I would have saw more of that. And an important clarification is this approach is different from making robots robust to human mistakes by always acting in a risks-averse way. So this was actually really helpful for me. I almost assumed while reading this paper that, so this model just makes, like, let's take the autonomous driving, for example. It's just going to make every human drive like a cliche grandma, super passively and always acting risk averse, when that's not the point of this paper. The point is to predict humans making risk averse decisions. So limitations. Overfitting this model is a concern due to the lack of data surrounding humans making suboptimal decisions, and that the model must understand the rewards and probabilities of the situation beforehand. And a little bit of clarification here on what overfitting is. So let's say you had a convolutional neural network that what you wanted to recognize the difference between a cat and a dog. And in that, what you fed in that neural network to train it was you gave it, let's say, 1,000 pictures of cats and dogs, and each picture of the cat and dog, they were laying on the grass. There's one cat laying on the grass and one dog laying on the grass, just different types of dogs in different ways. So what you'd find would be that while you're training this model, you're going to say, wow, it's got 99% accuracy picking whether it's a cat or a dog. But the second you feed it a picture of, let's say, a dog sitting on a couch, it'll probably get that wrong, or the accuracy will be way lower. And you'll be like, what the heck? My model was at 99% accuracy. But the reason why it failed was it actually didn't have enough data. It only saw a dog laying on the grass, so it got confused. And so now here's where it comes to my opinions and my thoughts. So and my thoughts relative to trust in human-robot interaction. So let's take a look at society's perspective. The current mainstream perspective, which I think is bad right now, is I don't trust autonomous vehicles or robots. They're dangerous. And we can see the Tesla here crashing into a truck. And what the point of this picture is to show you that every time the media really hops on Tesla and these autonomous cars and these robots as bad things, I feel like there's a bad light shed on them. When I feel like the media, it would be a good thing where if the question was, instead of saying this, we could say, well, how are we going to integrate with robots? What's the solution? Instead of saying they're bad. This is unpopular, but the good thing. And as you can see, I chose this picture because this is society where we ask this question. We got robots acting next to humans, and everyone's happy. So again, to expand on, so how are we going to fix this? What's the solution? Well, let's take a look at George Hotz. He's a autonomous vehicle entrepreneur. He developed a $1,000 camera solution to autonomous vehicles, where basically you can buy a camera and make your car autonomous that wasn't previously autonomous, and it's about the same level of autonomy as Tesla. So let's take a look at what he has to say. He's pretty smart.
But yeah, we think level 3 within 3 years is actually achievable. The definition of level 3 that we're using is every time the car is going to make a mistake, which it may still make mistakes, but it knows it in advance. The problem's not hardware, you know.
So he said two things. The first thing is embedded in the definition of level 3 autonomous vehicles, where he said the car will recognize a mistake even though it may still make a mistake, but it will recognize it before it happens. So it will basically, you can relate this to the risk-aware model, correctly predicting the human before it happens. And so as you can see, an application for how do we improve autonomous vehicles or autonomous robots. And another interesting thing he mentioned was it's not the hardware, it's the software. And I totally agree. His solution is just deep learning, just a ton of deep learning, and he's got me sold on that. I agree with that. But how? So how are we going to integrate with robots. And this is my concluding side. And what's the solution? Well, this is up to us. As engineers, we have to develop this technology and explain it simply to people. We have to develop it safely and efficiently. And when I say explain this simply to people, the point is autonomous vehicles and robots are so complex and really hard for people to understand, especially people that aren't engineers and aren't super technically savvy. And that's going to be a huge thing to increasing people's understanding. And that's my presentation on human-robot interaction and how trust factors in.